third order system, nice, simple, straightforward one. What we got here? Here we go. I put it in what form? Control form. Okay? So very simple, single input, single output system. Talk about multiple outputs in a second. And let's say we want to design a controller for this thing. And so I have, for my, we're decided where I want my poles. In fact, maybe the one thing we should do is get where the poles for our original system are. They are all stable at minus 3.27 complex pair here, so it's a bit oscillatory. So let's say I don't want my poles at minus 2. Numbers.
Yeah, you're signing in the wrong spot.
I knew where I wanted to put it. Why didn't it? I hate that computer. That's pretty good one. Okay, I think we got that right. So we're going to find a gain. I'll call K. And I'll use acronym for this. I do A, B, P. And there'll be some gains here. Okay? 7, 8, 6, 3, 1. So this is the gain for the first state, second state, third state. Assuming those are truly the states that I'm seeing. All right? Not things from transducer itself. Say I want to get a step response to this. How can I do that? Any thoughts? I want to simulate my system. No? What's the closed loop state equations for this system?
Bottom row of A.
Why A? I want the closed loop state equations. What are they? What's the matrix? The closed loop system.
Oh, it's A minus B.
Yeah. A minus BK. We've also kind of ignored this next part, but what would be the multiplier to an input, U? G?
D, yeah.
Doesn't change. Okay. How about the output?
Oh,
CX.
Still C times X, yeah. Plus B times U. Okay. But the only thing really changed is my A matrix. Now, when we talk about different types of inputs to this system, we're going to be adding stuff out here before I get something about that. Okay. So the roots of A minus BK should be these roots. Right. Let's do that. I'll call this A closed loop. A minus B times K. There's a closed loop system. Okay. What do you think the eigenvalues in this are? Minus 2 minus 5 minus 8. Right? So, yeah, that closed loop system should do that. Let's call this CL, and this will be state space A, C, L, comma B, comma C, comma D. This is my closed loop system. Okay? This should have this. The scaling will be off on this because I haven't compensated for the gain. That's okay. for a second, tries to find where it's got function are. Still thinking. I was thinking. Yeah, yes. Okay. I have this as a step response. Okay. Seem reasonable for those poles? Well, the poles are all what? All real. The closed loop roots are all real. Would I expect overshoot with all real poles? No. It looks pretty reasonable. I can check what the rise time is or so for this thing. Okay. Go look at that. All right. Make an observer for it. Where should we put the observer poles? They need to be what compared to my controller poles?
3 to 5 times?
3 to 5 times faster of the closed loop ones, really. I open loop ones too, so let's say 5 times. Okay. So they're my desired closed, observer poles. Right? And the homework you're doing this time is simply, here are the roots, kind of observer poles are. Okay? I have those. Can I get the observer gains now? Yes. I'll call this, most of these called L. And I use acronyms for this. But why am I going to put in acronyms for the observer?
The transfer of all of them? The transform of all of them?
Transpose.
Transpose, that's right.
Yeah.
Transpose.
One of those words. I got.
Yeah. That's one of those.
A transpose. Right? And notice that's the original open loop A matrix, not the closed loop one, but the open loop one. Because I'm trying to estimate what that open loop length is. All right, so let's get back to C transpose. And line poles. So there are my observer gates. Okay. Grab that one. Really the same thing. And we could check what would be the observer A matrix for this. Call that. A observe will be equal to what? Remember that one? A minus not CL, it has to be LC. In fact, L, wherever the L transpose. That, oh, yeah, over there, but let's check. Active values. Observe. Or where we want it, right? Minus 10, minus 25, 40, yeah, minus 40, minus 25, minus 10. So they're indeed in the right place. Now let's make the controller observer. Combine this thing, it's called the regulator. We went through what the structure that is there, but that is a really nice way of doing this. It does all the calculations for us. I'll call parse this is equal to a program called reg. And what we give it is our original open loop system, which I call sys, our controller gains, and our observer gains. Now, the way I have to do, I have to put this as a transpose for the structure. So this is our regulated, our should be the whole controller observer. Now, let's see. So, this is the observer A matrix, right? B matrix. Look at something right here, the C matrix. Does that look familiar? I mean, I memorize the numbers. Let's see what those numbers are. K is 78, 63, 11. 78, 63, 11. Those are the controller gains. Does that make sense to you? Think what's going on in the picture. Now I've got this controller observer. Here's my plant. Outputs Y. It's going into this observer. The output of the observer should be the estimates of the states, which go into the controller gains, which create U. Right? What we've done is combine this whole thing. The input to the regulator is what? Y, the output of the system. The output of the regulator is what? U inputs the system. So my system inputs U, outputs Y. The controller observer inputs Y, outputs U. It's the opposite. Right? And this whole thing is set up as a state system. So think of it, does it make sense that this would be like a C matrix? Because the output U is equal to, let's say, C of the observer times X estimate, which is what? Okay. The controller gains. Here indeed are the controller gains shown up here. Negatives of them. The one thing that this thing experiences is positive. So, sort of clear? What you're going to put into the lab system is this. That A matrix, B matrix, C matrix. We have to figure out Simulink how I can do that. It's really pretty simple because Simulink has what? You can put in a state system. So you can define a whole state system of A, B, C, D, put it in there and it'll calculate it for you. Life has gotten really nice with Simulink. All right, let's find the whole system. As opposed with 2. How can I get now the closed loop system whole control, original plant with control observer? What is that? What would I use to find that? Well, that's the forward path. That's the feedback path. And how do I need MATLAB to forward path and feedback path, combine it to the closed loop system? Feedback. One warning when you do this, here's my plant, my open loop system. My feedback is what I call R system, but I have to name minus R system. Because regulator assumes I have positive feedback. When I do regulator, it is assuming plus sign. So I have to put a minus sign down here. All right, let's see what that looks like. What order is this going to be? You wild guess? 6. Because I have the plant, which is third order, and the observer, which is third order. So now it's a 6-order system. Look at this. What's that part? That 3 by 3 up there. It's the original A matrix. The rest of this is a little bit tricky to see the controller gain showing up here. This is the original D matrix. This is the B matrix for the estimator, which is going to be zeros. Remember that structure we showed last time. And the C matrix is really the original C matrix, the estimated parts all is 0. Okay? Makes sense? This, or a little bit? What? It's supposed to have response to this. Now, the scale will be now the blue one was my original one, and the green one is the control observer. They're off by scales because I haven't rescaled anything here. I just said, this is a 1, right? But I really need to rescale because I have non-unity feedback here. If you look at similar, well, one thing you might see is that the, I'm trying to do some scaling. What's the ratio of these things? The red one is a rescaled blue one to be match the DC gains. Right. The green one is, so this is just straight feeding back to the state controllers gains. Right. So take all the states, both point times tag in my system. The green one is the observer estimating the states and then feeding it back. Notice it's a little bit slower. Right? Does that make sense? Yeah, because it's trying to calculate an estimate of what these states are, and it takes time to do that, so it's a little bit slower system to do. That's why you want those observer gains very much slower than, or faster than the controller gains. What would happen if I made them the same? Let me try this.
We're missing an A in Acker.
They have these irritating spell checks and grammar checks and things, but they don't do it when you want it. Especially on cell phones. You know, it's like trying to do a substitute. They don't ever change it because it still insists you want that word. All right, so let's find Q.